All right, we're working through the review for Math 1324, Test 1. To begin with, we're starting with two questions on domain. First, we have a polynomial, f of x equals x cubed minus 3x squared plus 8x plus 1. Because this is a polynomial, we know its domain is all real numbers. And that's all we have to do there. Okay? So we recognize what type of function it is first, and then that should help us identify what the domain is going to be. In the second part B here, this is a rational function because it's expressed as a fraction. And so because it's rational, we have to look at the denominator and figure out what value of x makes that equal 0. So we'll take x minus 3 equal to 0. We can add the 3 over, and that gives us x equals 3. And we have to be careful because that's not the domain. 3 is the number that cannot be in the domain. So the domain is all real numbers except 3, or we can more briefly say x is just not equal to 3. Okay. Adjust my camera a little bit. There we go. All right. The owners of a parking lot have determined the weekly revenue and costs for long-term parking customers can be represented by these two functions for revenue r of x and cost c of x. So we want the break-even point. Now, break-even means that they're neither making a profit nor a loss. That means revenue is equal to cost. So that's where we begin. R of x has to equal c of x. And so we'll set 80x equal to 50x plus 2400. Okay. And so we go ahead and solve this. We subtract over the 50x. So that leaves 30x equals 2400. And then dividing by the 30, that means if we can sell 80 items, then we anticipate being able to break even, at least under this scenario. So 80 long-term parkers in this case. Okay. Find the vertex of the quadratic formula. Determine whether it opens up or down. Now, first of all, the vertex, and we have this formula on the formula sheet. That says, well, here's our formula, and HK is the vertex. Okay. Now, if this is x minus h, notice this corresponds to a positive h. So whatever number we see here, this is actually the opposite. K is just k. That stays the same. So our vertex in this case is 3, 4, opposite of the 3. Essentially, this is the number that makes the parentheses equal to 0, if we want to think of it that way. And then the 4 is just by itself. That's our vertex. And then whether it opens up or down depends on this number in front. Now, our 2 is positive, and so because that's positive, we can say that this is going to open up. And so that's our response here. So if this had been a negative number, it would open down instead. Okay, find the equilibrium quantity and price for a commodity with these supply and demand equations. It's similar to a break-even, because if we want equilibrium, that means we want where the two equations are equal to each other. So it's a similar process. We set them equal to each other, but unlike our break-even formula from problem 2, this one has a square on it, so it's going to be quadratic. Now, q squared plus 300 equals negative 5q plus 2100. Now, if we're going to solve this quadratic equation, we need everything over to the left-hand side equal to 0. We want the q squared to be positive, but so we'll move everything to the left. So we can add over 5q and we'll have to subtract over the 2100. And so that's going to give us q squared plus 5 times q minus 1800 equals 0. Now, 1800, not an easy number to factor. And so if you look on the key that I posted on earlier this week, Wednesday I believe it was, I went through the quadratic formula here. Now, if we do recognize how to factor this, then that's an option as well. So the main thing here is trying to figure out, okay, what gives us 1800? Well, we know it's 100 times 18. We also know it's 50 times 36, 25 times 72. None of those seem to be working. What else do they have in common? 10 and 180, that's not going to do it. 20, oh, we can do 30, and so that'd be 60. It's got to be a closer pair. 45 times 40? Yeah. So that's it. That's actually the combination that we need. So it's q plus 45, q minus 40 equals 0. Okay. We need them to be opposite signs to equal a negative product, and they have to add up to the 5 in the middle. So we can do this as an option, but if you want to see the how it works out with the quadratic formula, then that's on the copy of the key that I had posted earlier in the week, which ultimately that may be the better approach. Anyway, the point is here we get two possible solutions for equilibrium, and Q is quantity in this case. So either we can produce negative 45 items to break even or have equilibrium, or we can produce 40 items and have equilibrium. So unrealistic to have a negative answer, and so that just leaves us with Q equals 40. So we know that it takes 40. 40 is our equilibrium quantity for supply and demand, so that gives us a best case scenario. And then we just take that and we plug it back into either one of our two equations, whichever one seems like it might be easier to use. I'm going to go with the supply. So P is equal to Q squared plus 300. There we go. We'll plug in our 40. So it's 40 squared plus 300. So it's 1600 plus 300. So our equilibrium price is 1,900. So that means we can, if we can produce and sell 40 items for $1,900 each, whatever this is we're talking about, then that puts us at equilibrium where our supply and our demand are in harmony. So, okay. Now, number 20, suppose that the price of an item can be determined. We have a price function, P of X. We also have a fixed cost and marginal cost provided. So Let's take our fixed cost and marginal cost first. Well, our fixed cost is $12,000 and our marginal cost is $200. So C of x is 12,000 plus 200 times x. We just put the two numbers together just like that. Revenue, R of x, is going to be x times P of x. That's our price. So x times the price is our revenue. So we'll plug in negative 4x plus 800 for P of x. And then we just have to distribute the x here, so it's negative 4x squared plus 800x. And so that's R of x. Okay. So we found cost and revenue, C of x and R of x. So now part C, they want us to find profit. Let's come down here. So our profit, P of x, capital P of x now, not lowercase p, that's price. It's a little confusing that we use both letters in the same set of equations, but you kind of get used to it, I guess. But revenue is R of x, P of x is R of x revenue minus the cost C of x. Now, R of x we found negative 4x squared plus 800. And C of x, our cost, is 12,000 plus 200x. Now we want to make sure we subtract that in its entirety. So I'm going to go ahead and put that in parentheses. Now, the parentheses here don't really do anything on this first term because there's nothing modifying it in front. So that's just a minus 4x squared plus 800x, which I had left off the x there, sorry. But now this minus sign has to distribute to both of the numbers in the second parentheses. So that's a minus 12,000 and a minus 200x. Now we can combine our like terms. We have an 800x and we have a minus 200x. And so that's going to give us negative 4x squared plus 600x minus 12,000. And so that's our profit function, capital P of x. Okay, so now we have a profit function. So next, part D, the number of items that will need to be produced and sold to maximize profit. If our goal is to maximize the profit, then that means we have to figure out where the vertex of this quadratic equation is. So it's maximized at the vertex. Here's the problem though. We talked about the vertex formula for a quadratic right here, but we don't have an equation in this format where it's something times something squared plus a number. Here, we're looking at a more traditional trinomial, just everything's multiplied out in just one string of terms. So in this scenario, the way that we find this vertex is our x is going to be negative b over 2 times a. And I'll make sure I include that formula on the formula sheet. It's not on the formula sheet I gave us for this review. I'll make sure I include it on the formula sheet for the exam, because when we definitely have a question like number 5 here on the exam. So a, b, and c, these are the three terms in our quadratic. A is the negative 4, b is the 600, and c is the negative 12,000. So negative b makes that a negative 600. And on the bottom, we have 2 times a, which is negative 4. So that gives us negative 600 over negative 8. And that divides out to give us 75. So that means if we can produce and sell 75 items, then we should achieve a maximum profit. Okay. But then the next part is, part E, what is that maximum profit? Well, to get the actual maximum, we take the x that we found and we'll just plug it back into our formula here for profit. So essentially, at this point, we're finding our profit function, capital P, evaluated at this value of 75. So this is just really a calculation problem now. So we plug that in, negative 4 times 75 squared plus 600 times 75. And then take away the 12,000. 75 squared is 5625. 600 times 75. The heck is that? 45,000. I need to get a calculator out. Anyway. And then negative 4 times 5625, that's negative 22,500 plus 45,000 minus 12,000. And so if we can combine all that together, that ends up being $10,500. So that ends up being our maximum profit. So the last question they ask us, or that I ask you, I wrote this question, the price that should be charged for this item. Well, now we go back to our price function that we first looked at. Little p of x is negative 4x plus 800. So now, we already discovered in part D that it's going to take 75 items to realize a maximum profit. And so the question is, well, how much do we need to charge now? Well, we take that 75, that same 75 we'd used in part E, in profit. Now we'll take that 75 and plug it into our price formula, because this will tell us, well, if we want to sell 75 items, this is the price that we should sell according to our demand equation. And so that ends up being negative 4 times 75 plus 800. Negative 4 times 75 is negative 300. And add 800, that means we should be charging $500 each for whatever it is that we're looking at here in this problem. So if we can sell 75 items for $500 each, then we can anticipate making a profit of $10,500 overall. Okay. So this is what's going to make the price now is what makes this all work, what makes this optimization occur. So we have to remember to find that as well. Okay. That was a long problem, but it does state that it's worth twice as much as any of the other problems. Okay, 6, we're talking about the average cost function. Now, C of x is our cost function. So C with the bar over it, we call it C bar. This is our average cost function, and this is defined as C of x divided by x. So it is a rational function because of that. And so if we just take C of x and then divide these by x, we can split it up. That's a 45x. So we'll take 45x over x, and then 3,000 over x. The x's cancel here. So C bar of x is just going to be 45 plus 3,000 over x. part B, they want us to evaluate C of 25. So we can plug 25 in here to our cost function. 45 times 25 plus 3,000, and we just calculate this out, and that's 1125, so 4125 total. Just putting that all together. Okay. So the cost of producing 25 items is $4,125. But then we also want the average cost for producing 25 items. So we take that same, or now we take the formula, C bar of x that we found in part A, and now we sub in our 25 for x. So that'll be 45 plus 3,000 divided by 25. So that's 45, and that's 120, so it ends up being $165. So it may cost $4,125 to make 25 items, but that works out to be $165 per item. Okay. And so that's what the average cost function represents, is the cost per item, where instead of just the overall cost, we're breaking it down on a per item basis, which is also useful information, because then we can use that to kind of help us with pricing or whatever else we want to do. Okay. Now in 7, we have a formula for a monthly payment on a car loan that earns, or that is purchased at 12% annual percentage rate on an unpaid balance. And we have a formula where P is the unpaid balance and N is the number of months over which the loan is repaid. So we have a vehicle that costs $15,500 and is repaid over 60 months, 5 years. So we'll plug in the $15,500 for P and 60 for N. So this is really just a computational problem. I mean, we have to get the numbers plugged into the right place, but beyond that, it's just calculator work. Okay. Now, on the numerator, 0.01 times 15,500 . 0.01 times 15,500. Okay, that just gives us 155. Now in the numerator, we have to do the exponent before we can do the subtraction. That's the standard order of operations. So we'll take 1.01 and raise that to the negative 60 power equals. It looks like it's about 0.55. So I'm going to put down 0.55 here. Now that's being subtracted from 1. So we're going to end up with 155 on top and then 0.45 on bottom. And now we'll just do this division. 155 divided by 0.45. And so we get $344, and we'll round it to 44 cents on the decimal for the monthly payment for this used car. Okay. We're going to talk about a lot more of these problems after our exam when we get into that Chapter 5 material. We'll talk a lot more about compound interest and things. So this formula is just a simplification of a more complicated formula that we're going to see later on in Chapter 5. Okay. Now we get into Chapter 4 problems, talking about these logarithms. Now, problems 8 and 9 use what we call our conversion formula. Now, our conversion formula says that if y equals log base b of x, then we can convert that to b to the y equals x. This is one of our formulas back here on our formula sheet. There's a conversion formula. I'm going to clean up the formatting here because I wasn't happy with that space. But anyway, I don't know what happened, to be honest, but I will definitely fix that before I print out the actual exams. So now, one issue we run into this problem is there is no base listed. Now, there's two scenarios where the base will not be listed. One is if we have the natural log of x, that is log of base e. Okay. And the second is if we have log x, which we do have here, this is log base 10 of x. And so there is an invisible 10 there that we have to be aware of. But more importantly, that's our b value here. So it's like we have y is 4, b is 10, and x is just x. So now we rearrange them in this order. B first, raised to the y. So 10 raised to the 4 equals x, which is still just x in this case. And then if we take 10 to the 4th power, that's going to give us 10,000. So we end up with 10,000 equals x. And so that's actually how we solve an equation like this, is by converting it from log to exponent form. And that's what lets us calculate the value of x. Now 9 is basically the same problem, but now going the opposite direction. Now we have an exponential equation. We have, let's say this is in the form b to the y equals x. And now we want to make it y equals log base b of x. Okay. Now, here, converting this, again, it's just a matter of lining up our terms, like b is 5, y is x, and x is 15. It's a little bit confusing that we say y is x and x is 15, but we have to kind of go with that. Now, our y, that's x. So we convert this, we get x equals log our base b, which is 5, and then our x, which is 15 in this case. Okay. So we know x is equal to log base 5 of 15. Now the problem we face here, because we do want to be able to calculate the value of x, is we have to essentially take a log of base 5. Now the problem is, the reason that these logarithms don't have bases is because these are the two functions we can do in our calculator, natural log of x and log of x. So if we don't have one of those, then we can't just put it into the calculator. And so for this problem, we have what's called the change of base formula. And that says log base b of x is equal to log of x divided by log of b. Right? So x is equal to log, and we'll take the 15, whatever x is here. So here's our x, here's our b. So we take log of 15 over log of 5. And so now we can do that in the calculator. So we'll take log of 15. Now in this calculator I have to press the 15, and then the log button. Then I'll hit divide, and then the log of 5, so I press 5 log, and then equals, and there's our result, 1.683, let's say. We can round that to 2 or 3 decimal places. That is sufficient whenever we do need to do any rounding here. We know if it's a dollar amount, we can round to 2 decimal places very clearly because that's how we deal with money. But something here where it's kind of unknown what we're looking at, maybe we can go to a 3rd decimal place. But if you just put 1.68 here, I would still count this correct because everything we've done is correct to get to that point. And it's just a question of how far do we actually need to round it. Okay. Problem 10. Use the properties of logarithms to expand and write the expression in terms of logarithms of x and y with each variable of the first degree. Now, for this one, we are using our log properties. The problems on this page come from that it was a day that I was absent, but I had requested y'all watch some videos online for that material, and so all this content is in those videos that we went over, that I had you go over. So here's our change of base formula, as I mentioned, and then we have our log properties. We have a product rule, we have a quotient rule, and we have our power rule. I believe I talked about these again on Monday this week. Anyway, so we have our product rule, quotient rule, and power rule. So depending on which one we have, we know we can manipulate the formula in a particular way, or we can manipulate the expression in a particular way. Now, first of all, the first thing we see is that we have division here. So with that division, we know we can apply the quotient rule first. And the quotient rule says we can take the log of the numerator minus the log of the denominator. Okay. So that's just the quotient rule being applied. And you don't have to write down what rule it is. I'm just leaving it there as a note for us to see, hey, this is what we did here. And you might have noticed that on the key that I had uploaded for this earlier this week. Next thing is we have a product here. We have 3 multiplying x squared. So using our product rule, we take the log of the first term there, 3, plus the log of the second term. Okay, so we take the log of 3 plus the log of x squared. And we keep the other log as it is. Now, I did make a slight change here because I know what's going to happen next, and I wanted to save writing down an additional line. But square root of y, it turns out, can be rewritten as y to the 1/2. The reason we would want to do that is in the very next step, if there's any exponents inside of these expressions, we need to factor those exponents out to the front of those logarithms using the power rule. So that's our next step, is this one, because of the power rule, we can take our 2 and bring it out as a coefficient. Take our 1/2 and bring it out as a coefficient. So this is 2 log 3 of x minus 1/2 log 3, I left off the 3 there, sorry, of y. Now when there's not just one term in here, we don't necessarily have to put it in parentheses, but that's what I've been doing here. There is one more thing we can do in this case, and it's not immediately obvious, but we have log base 3 of 3, and so just like we did here in our previous example with our change of base formula, we can change, if we have a base b of x, then that's log of the x here divided by log of the base here. So we can make this log 3 over log 3, but that just works out to 1. So we end up with 1 plus 2 log base 3 of x minus 1/2 log base 3 of y. And so that's our solution to this. So we've expanded this logarithm out using our properties. So not only do we use all three of our rules, we also use our change of base formula in the process to arrive at this conclusion. Now, one of the reasons I include this problem on the test is that we do have a similar problem to this on the final exam. So I want to make sure we practice it here, practice it on our, utilize it on our exam, and then hopefully be in, have a little bit better understanding so that we can do the same whenever we get to the final. Okay. So 11, we want to solve the exponential equation. 3 to the x squared minus 2x equals 1. Now, one option we have here is to convert it. The second option, which we generally prefer in mathematics courses and applications of mathematics, is in these exponential equations, go ahead and take the logarithm of both sides. We introduce the logarithm, and I'm just going to put a logarithm of base 10, so we don't have to put a number down here or anything. But we just take a logarithm and apply it to both sides of this equation. Now, the interesting thing here is on the right-hand side of this particular problem, if we take the log of 1, it's just 0. It turns out log of 1 is 0. Which actually helps us a whole lot in this problem. Because now we can have our exponent and factor that out to the front. That's our power rule again. So that's x squared minus 3x log 3 equals 0. And at this point, we can divide by log 3. And it turns out it doesn't even really matter what log of 3 is, because 0 divided by anything else is just 0. So at this point, we have x squared minus 3x equals 0. And so we just have a quadratic equation to solve. Now this quadratic equation, we do have a common factor we can take out from both of those terms. If we can factor out an x squared divided by x is x. 3x divided by x still has 3. So we're undistributing the x now. And so that gives us two possible answers here. X equals 0 and x equals 3. And so this one happens to have two solutions. Now, not all of these problems that we see here on the review are going to be on the exam. The review, I think, is 14 problems, and the exam, I think I reduced it to 11 or 12 problems. So 2 or 3 of these questions are not going to be represented on the exam. 11 here, maybe one of them, I'm not sure. I'm still going to spend a little time to pick and choose here and make sure it lines up with what we see on the final exam also at the same time. Just so I don't want to leave anything out that's going to end up on the final. Also because we want that extra opportunity to practice and perform in those. So, okay. 12. We have a logarithmic equation now. Now, if we have a logarithm equal to a number, and we have equal to a number here, as we see, then our process is basically like what we saw on the previous page on number 8, which is to take this logarithm and convert it to exponential form via the conversion formula. This problem 12 is a little bit different though, because we start off with a pair of logs here first. So step 1 is to combine these together, and that is the product rule. So we're still using our log properties, okay? And so combining those, that'll be log base 2, and we just multiply whatever is inside, which in this case is the x plus 4 times the x minus 3. Now we are ready to convert this. And again, when we do our conversion, it might be good just to over on the side put our conversion formula so that we can line up where everything, not y, I'm sorry, x. So we can line up where everything has to go. Okay? So here's our b, here's our x, and here's our y. Okay? So if we take b to the y, that's going to be 2 raised to the 3 power after we convert this. And then our x inside the logarithm to begin with now comes over to the right hand side. So it's equal to x plus 4 times x minus 3. Okay. 2 to the 3rd power, that's an 8. 2 times 2 times 2. And on the right hand side, we'll go ahead and multiply everything out. FOIL that together. X times x is x squared. X times negative 3, negative 3x. 4 times x, 4x. And 4 times negative 3, negative 12. I'm going to go ahead and subtract our 8 over at the same moment. And so we end up with 0 equals x squared plus x minus 20. Now, we have to solve this quadratic, and again, we could use the quadratic formula if we really needed to. It's going to be so much better if we can actually just factor this, though. Now, in this case, if we're looking at factoring it, we want two numbers that multiply to a negative 20 and add to a positive 1. Okay. So we know it has to multiply to equal this number and add up to the middle number, or the b value. So that's our c, that's our b. And so we think about, okay, well, to multiply to a negative number, we have to have a positive and a negative, and they have to be basically 1 apart. So that's 4 and 5. Okay, so we know it's 4 and 5, but one of these has to be negative. That means if they have to add up to a positive 1, we're going to need a negative 4 and a positive 5. Like so. Now, that creates our factorization, and so we get two solutions, x equals 4 and x equals negative 5. But now there's a problem that we run into in this particular case, and that is that sometimes the solutions we get for these log equations are not always valid. And so it's important that, especially when we get two answers like this, there's a good chance that one of them is not actually a valid answer. So we go back and we talk about the domain of these logarithms. We know the domain of a logarithm is positive numbers only. Is we can take, if we take 20 and take the log, okay, we get a result. If we take 10, take the log, we get 1, okay. 1.58, take the log, okay, we're good there. But if we enter a 0 and take the log, it gives us an error. Cannot take the log of 0. If we throw in like a negative 5 and take the log, again gives us that error. We cannot take a log of a negative. So that's the issue that we're facing. So if we take our 4 that we got, our first solution was x equals 4, come back up to the original equation, 4 plus 4 means we're going to be taking log of 8. And that's fine. Log of 8 is a good number. 4 minus 3, that's a 1. Log of 1 is also a good number. So we know we're good there. So 4 checks out. Negative 5, though, let's plug that back in. If we plug in negative 5, negative 5 plus 4 means we're going to be taking the log of a negative 1. And we can't do that. We know that log of negative 1 is going to give us an error. So negative 5, while it came up as a solution to this equation, is actually not a solution to our overall equation. So in this case, we actually refer to it as an extraneous solution, or just it's a non-answer, basically. So we really only have one good answer here, and that's x equals 4. Now, if you got down here to the end, you just put both of these answers and then check, I'd still give you 9 out of the 10 points. But in order to be 100% correct, we have to go back and check our answers and make sure that we're able to evaluate the logarithms that we would need to evaluate to be able to plug these back in. Okay, and it just doesn't work for this negative 5 in this case. All right, the last two problems are applications. I'm thinking of getting rid of one of these two for the exam as one of the ones I get rid of. I'm going to look at our final and make sure there's one of those there that I need to keep. But anyway, first of all, the h of x equals 23.5 times 1.08x. In this case, h is the total expenditure on benefits for U.S. veterans measured in billions of dollars. And x equals 0 corresponds to the year 1990. So however many years have passed since 1990, that's the value of x that we use. So in question A, what was the total amount of expenditures in 2013? First thing we want to do is figure out what value of x corresponds to this year. So if we take away 1990 from 2013, then we realize, okay, that's 23 years after 1990. So the x value we use in this case is 23. So we'll just take this 23 and now plug it into our formula. And then it just becomes a computational problem. Now in our order of operations, we do our exponent first. So 1.08 raised to the 23. Raise that to the 23rd power. So 5.87 approximately. And then we'll just multiply those two numbers together. 23.5 times 5.87. And we get 137.95, let's say. Now this is a currency amount, and again, this is in billions of dollars. Okay, so we should put a dollar sign since it does refer to a monetary amount, and because it's not just $137.95, we should also follow it with billions, which is how this number is being measured specifically. Okay, the second part of this problem is during which year did expenditures first exceed 110 billion? Now we know by the year 2013 we're already at almost 140 billion, so it's going to be somewhere before the year 2013 that this occurred. So that should help guide kind of our answer here, make sure we don't get too crazy of an answer. Because if we come up with 45 years after, which would put it at like 2035, it would cross this barrier. We know that's not true because it had to get there to get here first. So anyway, 110 billion, that's our h of x. Okay, So we go back to our formula here. We'll take that 110 and plug it into the left-hand side of this equation, of this function. And when we plug it into the left-hand side, we don't plug it in for x, we just replace that whole thing with 110. Okay, so we have 110 equals 23.5 times 1.08 to the x power. Now, I would say, well, there's one step we have to do first, and that is we want to get the exponential portion, the 1.08 raised to a power, by itself before we do anything else. So let's divide by 23.5 now. So taking 110 divided by 23.5, looks like it's about 4.68. Okay, so here's where we are. We have 4.68 equals 1.08 to the x. Now, solving this, very similar to what we had done over here on number 11, where we take the log of both sides. Okay, we could also use a similar approach as on number 9, where we instead did a conversion and then had to use the change of base formula. So it's really a question of which approach we prefer, because honestly I'm not going to restrict you to either one of those approaches, but those are really the only two viable options that we have as far as solving this problem. Okay, so I'm going to go ahead and take the logarithm of both sides. And this is just log of base 10 because we want to be able to use the calculator here. So we have to use one of our calculator functions. Okay. And then our exponent can now be moved out to the front of the logarithm. So we'll say log of 4.68 equals x times the log of 1.08. And now we can divide by the log of 1.08 to get the x by itself. Okay. So now let's just calculate this result. We have log of 4.68 divided by log of 1.08 equals. We see there it's just over 20, 20.05. So I'm going to say x is right about at 20 years. Now, the question is, which year does that actually occur in? Well, remember that x equals 0 corresponds to the year 1990. So if we just add 1990 to 20, that means that this happens during the year 2010. And that's how we want to accurately express our answer here. It asks us which year did the expenditures first exceed 110 billion, so we want to make sure we answer with a year as a response to that. I'll still give you all but like 1 point of credit for putting 20 years down. We want to make that final conversion though. Okay. All right. Problem 14. Suppose the number of teachers can be approximated by this formula. T of x equals 1.5 plus 2.1 log x, where x is the number of years after 2000. In which year did the number of teachers surpass 4 million? Now, this is similar to 13b in that 4 million, the number of teachers, this is T of X. Okay? Because X reflects the number of years that have passed, and then the number of teachers, that's what T of X represents in this case. Now, the mistake I see a lot of students make is because we see this number 4 million, I see a lot of students put 4 million over here. But remember that this number is already measured in millions, so we only have to put the 4 there. So we have to be careful that we don't mislead ourselves interpreting that response when the number is already assumed to be in millions. Now, this problem will end up being a lot like number 8, I believe it was. In 8, we just had to take our logarithm equation and convert it to an exponential to be able to solve. But again, our conversion formula relies on having log base b of x equal to y. And we have our log base b, 10, of x, but we don't just have a y, we have like a bunch of other terms here still. So again, we need some preparatory steps before we can actually do any calculation or do any conversion. So first thing, let's subtract this 1.5 over. That gives us 2.5 equals 2.1 log x. And then we'll also go ahead and divide by 2.1. We'll take 2.5 divided by 2.1, so about 1.19 equals log x. And again, that's log base 10 if we wanted to go ahead and include that. Now, here, really our only choice of action is the conversion formula. So if we want, we can kind of write it down side by side and just line these things up. Here's our y, here's our b, here's our x, just to match it to this format. Okay. Now, b to the y, that'll be 10 to the 1.19 equals x, that's just x. So we get x equals 10 raised to the 1.19 power, and now we just do that calculation. 10 raised to the 1.19, and we get about 15.5. Okay. Now this is x. X is, in this case, number of years after 2000. And so if this 15.5 years after 2000, we just add 2000 to that, so it's the year 2015. And the 0.5 in this case means, well, probably June or July of that year is when that would happen. So we just would, again, want to translate this to a year. The main thing we need from that year is the whole number portion. The fraction means it's just a fraction of a year beyond that. So during the year 2015, that's our best response there. All right, we're basically right at an hour now of this video. Hopefully this has been useful and something that you'll find helpful in preparing for your exam on Monday. Now let me know if you have any questions, and yeah, be ready for it. And yeah, send me any messages if you do have questions. All right, have a good day. Bye.